Hello and welcome to Physics 1403, Stars and Galaxies. Today we're going to have a very short introduction to astronomy and some basic ideas about the universe, starting with where we are, our planetary neighborhood. We're going to start with Earth, our own planet, our home, and then the objects we see in the sky, the moon, the sun, and the other planets, our solar system. That's where we're going to start. So we're going to start with Earth. Earth is like a large ball, right? A sphere. It's not exactly a sphere. It means the radius at the equator, which is the large circle at its belly with some radius. This radius is not the same as the distance from the center of the Earth to, say, North Pole or South Pole. That's why it's not a perfect sphere, but for our purposes today, it doesn't matter. Let's say it's a sphere, a very large sphere, a solid rock on the outside. Inside we have a liquid magma and an iron core at the center, which is also solid. We have the mantle and the outer shell, and we have tectonic plates. We have a lot of geological activity because the Earth is still warm, still hot. Okay, Earth is around 4.5 billion years old. Billion years old. It's pretty much the same age as the solar system, and we find this number using nuclear physics, using radioactive methods, not only using the rocks we have on Earth, because they're subject to change over centuries, but also the space rocks that have hit the Earth in the past. The older the better. So the number is around 4.5 billion years, just a little bit younger than the Sun, which is less than 5 billion years old, pretty much. But this is the age of our solar system. So Earth is roughly a sphere with some radius. Now I'm going to use an average number here. And I'm going to use a symbol, which is a cross inside a circle. That means Earth. So this radius is 6,371 kilometers. Let me pause it for a second. Okay, sorry about that. I had to let the cat out. So the Earth radius is 6,371 kilometers. Well, you can convert this to miles if you like. You will need a conversion factor. 1 mile is 1,609 meters, which would make 1.609 kilometers. So if you want to convert the radius of the Earth, this number, to miles, you would just have to multiply this by a conversion factor. What is a conversion factor? You take this equation and you divide both sides by, let's say, 1 mile. And then 1 mile. Okay, then it will give you 1 here, and then this equal to 1. Or you would divide both sides by 1.609 kilometers. Then the right hand side will give you 1. That's another conversion factor. Both are equal to 1. Any number multiplied by 1 is still the same number, right? That's why we're going to place it here. 1 mile divided by 1.609 kilometers, so that the kilometers will go, and then you will have the answer in terms of miles. So 6,371 divided by 1.609, 3959, about 3,960, approximately 3,960 miles. Okay, 3,960 miles is the radius of the Earth. Now, I mean, you can find numbers online, the radius at the equator or some average radius, but let's stick with this number for now. This will give us an idea how big Earth is, right? And the second thing we can consider about Earth is its mass, all right? Its mass. So how much rock we have here, either solid or in the form of magma. M stands for mass, and M with the symbol for Earth here. So this number, you can look it up, it's 5.97 times 10 to the power 10 to the 24th power in kilograms, okay? Now, how do we have these numbers? I mean, of course, you can Google them, but why? I mean, is there a way to measure them, right? Actually, believe it or not, these numbers have been around for a long time, especially the radius of the Earth. It's been more than 2,000 years. I mean, it goes all the way back to the classical age, like the classical antiquity. We're talking about the Greek philosophers and Greek mathematicians. Classical antiquity. So the first person, as far as we know, who calculated the radius of the Earth or circumference, they knew Earth was round, was Eratosthenes. Okay, this is maybe 200 years before Christ. So he lived in Alexandria, Egypt, and he's the first person to measure the radius of the Earth very accurately, actually. And he used a very simple method, which you can even do today, all right? All you need is a friend who lives, let's say, north of Houston, all right? Here in Houston, that's where we are. Go up north on I-45, let's say Conroe or Huntsville. Huntsville, okay, which is north of Houston. So call your friend there, okay? All you need is a cell phone and a calculator will help you. And a piece of stick, okay? Take a meter stick. So take a stick and call your friend to do the same. Just stick it on the ground at noontime, let's say, when the sun is at the top. And of course, the stick will, on a clear day, will have a shadow on the ground. All right, just measure the length of the shadow and let your friend in Huntsville do the same. All right, but you guys have to use the same stick or sticks with same height. All right, and then measure the length of the shadow. And from this information only, and also you know how far Huntsville is from Houston, you can determine the radius of the Earth. It's really simple, actually. So let me try to draw a picture here. So this is Earth. I'm not going to draw sun here. Sun is really far away and it's much larger, but I know the light rays that come from the sun, by the time they reach Earth, they look like these, right? I mean, the sun rays of sun are parallel lines. Of course, when the light leaves the sun, they leave in all directions, but from the viewpoint of the sun, if you were able to look at the Earth from the sun, Earth is a small dot really far, okay? So it's a really narrow angle we're talking about. So we don't have to worry about the light rays which are spread. The ones that reach us, okay, are within, 2R distance. So in that range in the sky, those lines are pretty much parallel to each other, okay? So Eratosthenes used the same logic, okay? So here's what we did. Now, let's say we are here in Houston. Okay, so this is Houston. I'm going to try to exaggerate it, okay? This is Houston, where we are. And then here is Huntsville. Okay, Huntsville, H bar, that's Huntsville, right? Now, the stick we have, let's say meter long stick, okay, it's upright. All right, so this is the stick. And here in Houston, we have the same situation. Our stick looks like this. Now, the shadow, right, the shadow on the ground, let's use red to show the shadow. So look, the light ray is coming like this. So the shadow on Earth will be here. Okay? That's for Huntsville. But where we are, the south of Huntsville, Houston, the shadow can be found the same way. This is the light ray that comes, and the shadow is right here. But this shadow is shorter than the shadow our friend in the north would measure. Okay, so we're going to use that. That's how we're going to find that's how we're going to find the distance. I'm sorry, the angle here. Let's give it a name. Okay, so this is the radius of the Earth that we're after, right? R, which is the same, of course. We know the distance between Houston and Huntsville. Let's give it a name. Let's call it D, distance. D for distance, all right? So here's what we have. We have a triangle right here with an angle, and we have another triangle with a smaller angle, right? Call this angle theta, or theta 1 if you will, and this is theta 2, right? Of course theta 1 is a little larger than theta 2, and if you extend this line here, by the way, this is a 90 degree over here. That's also a 90 degree. But you can think of another triangle, larger triangle with the right angle right here. And there's also a triangle, this triangle, right? And then there's that triangle. So the knowns. The knowns are the height of the stick, call it H, right here H. We know the length of the shadow, call it shadow S, S1, and then S2. Now the H is the same for both, of course. And using simple trigonometry, like tangent, right, use tangent. Tangent of theta 1 is the side opposite divided by side adjacent, right? So S1 divided by, not D, I'm sorry, H, right? Similarly, tangent theta 2 is equal to S2, that is this side, divided by H, right? So using your calculator, you can use the arctangent and find those angles, theta 1 and theta 2. And once you determine those angles, this means you know these angles here. This is 90 minus, what is that? 90 minus theta 1. And the larger angle here is 90 minus theta 2, okay? So you can subtract the smaller angle from the larger angle to find that alpha that we were looking for. Alpha would be 90 minus theta 2, the large angle here, minus the smaller one, which is 90 minus theta 1, right? So 90s go away, that's pretty much theta 1 minus theta 2, the difference between the two. That's our alpha, right? And you just multiply that alpha in radians, not degrees but radians. Multiply that alpha by r to get the distance between Houston and Huntsville, right? Or solve this equation, let's say, and that's the radius of the Earth divided h bar or h prime. What did I call it? I called it h bar, right? The distance between the two cities divided by that angle in radians, which will give you the radius. Okay, so what Eratosthenes did was even simpler actually, all right? I mean, he didn't have a phone, he didn't have a friend to call, he just had to go there and do the experiment himself. What experiment? The shadow experiment. And it was even easier in this case because he used the fact that a certain time of the year the sun is directly above. All right, so here's the Earth again. Now, this did not happen in Alexandria, where he lived. Alexandria in Egypt. So let's say that's here. Alexandria, Egypt. So he can put a stick here and measure the shadow, right? Just like we did in Huntsville. But he traveled south down the river Nile and found a place where the sun is right above the sky. Okay, so it's like this. There was a well, a water well. Okay, the water well is here, and there's water in the here and in the bottom, and the sun, you could see the reflection of the sun at the bottom of the well. So he knew that the sun was right above. Okay, this is the ray. So all he had to do is actually measure this angle here, alpha. Now these two lines are parallel, which means this will also be equal to alpha, right? So he knew how far that city was from Alexandria in miles or whatever unit they use at the time. Okay, so he had the distance here and he had the angle. He just solved for the radius. All right, so the number he found is really close to the number I just gave you, which is 6,371 kilometers. Maybe he found maybe just a little bit less than this, but it was very accurate. I mean, this was more than 2,000 years ago, all right? Eratosthenes. And since then, I mean, we calculated this with better accuracy. What about the mass? I mentioned the mass, right? 5.97 times 10 to the 24th kilograms. How do you find this? All right, there are many ways, especially today with all the equipment we have. But that number was also discovered a long time ago in the 18th century, you know, in the 1700s by Cavendish. He did experiments. The Newtonian theory of gravity was around. So he did some tests. Isaac Newton had discovered his theory of gravity, and Cavendish did some experiments, okay? Newton did the mathematical work, and Cavendish did the experimental work. So he calculated the mass of the Earth. How did he do it? He took a piece of wire. So he hung the wire from the ceiling of his lab, and he tied that wire to a piece of stick. I mean, he did better than that, but I mean, I'm just simplifying it. Okay, a really long rod from the middle, so it's in balance. And at the end of the rods, he put some heavy objects like lead balls, let's say. All right, really heavy. So if you just leave it like this, it stays in balance. We call it a torsion balance, actually. This thing is called a torsion balance. Okay, it's not only balanced this way, but it's also balanced that way, because the wire acts like a spring. So if you try to rotate this either way, clockwise or counterclockwise, okay, the wire itself will experience or react with a force, all right? A restoring force, as we call it. So you turn it a little bit, and then you let it go. It wants to go back to the initial shape. It won't stop there. It's going to go a little bit further and coming back and forth. It's going to oscillate for a while until it stops, okay? So it's a balance, not only in this direction, but also that direction. All right? It's called a torsion balance. So he used this to do what? To measure gravity. So he added to the system two more masses, maybe larger, okay? One here and one there. So these are all made of lead, very dense, heavy balls, and they're all on the same plane, all right? Maybe he attached these to the walls of his lab. Doesn't matter, okay? But what happens is there is a force of attraction between those objects. Now you don't have to worry about the force of attraction between, let's say, the small lead on the right and the large lead on the left, but the ones that are close to each other, that's the one that you should worry about, because gravity decreases by distance, or the square of distance, okay? I'm going to show the force between these two as arrows, like these, and between those two also, there's force, okay? Force, let's call it F. F stands for force, okay? So Newtonian gravity tells us that any two objects with mass will attract each other. Now, can I feel it? Like, does this calculator attract the phone? And vice versa? Yes, they do. They do attract each other, but I will never be able to tell it or feel the force because it's so weak. Gravity is the weakest force you can think of. Okay, there are four fundamental forces, and gravity is the weakest of all of them. And the interesting thing is, gravity is the only dominant force if you look in nature or universe over large scales, like the motions of the galaxies and the attraction between planets and stars is all about gravity, not electromagnetism, right? Anyways, let's not digress. So he measured the force. Why? Because if these are attracted to each other, there will be a very tiny change in this force within the wire, okay? This torsion, because of the torsion. So that's measurable. I mean, if you do it in a very good setting, you don't let any external factors mess up your experiment, like wind, even a small wind. If you blow on it, it may change your setup, right? So you have to be very careful. He did this experiment, and he knew what the force between those balls and the Earth were. I mean, you can't feel the force between these two objects, but if you replace one of them with a large object as large and massive as the Earth itself, you start feeling the force, right? So he knew what the force on, let's say, this lead ball here, exerted by the Earth. This is exerted by the Earth, which we call the weight of the object. And we also have the other force, which is exerted by that large lead ball. And he could measure these forces. And from that, since he knew that from Newton's theory, the other part of the force equation has to do with the mass of the Earth, he found the density of Earth. Density has to do with how much mass you have in a unit volume. So you take the mass of the Earth and divide by volume. Now volume can be found because we have the radius, remember? And then 4/3 pi r cubed gives us the volume of the Earth, pretty much, approximately. If you can calculate, or if you can measure, a better word, measure the density of the Earth using this torsion balance, you can get to the mass of the Earth from that simple equation, okay? So today in physics courses, the Cavendish experiment is brought up in the context of a gravitational constant. Okay, the value today, the way we understand it today is, and the modern versions of this Cavendish setup experiment has to do with determining that constant called capital G, the gravitational constant. A very small number, but measurable. But at the time, in the 18th century, when he did it to determine the density of the Earth, because that was important. I mean, this was the beginning of geology. You know, the radius of the Earth. Okay, what is the mass of the Earth? Well, I have to find the density. All right, that's the thought process he had. So he did it. He found it. It was not a bad number that he got. But today we have other methods. Okay, and you can find Earth's mass many ways. I mean, especially those gravitational constants are readily available. You know, I mean, every time you weigh an object with a bathroom scale, you weigh yourself, and even from that measurement you can determine Earth's mass. Or if you want to do it in a fancy way using college physics, you can look at the motion of the moon around the Earth. Here's Earth, and here's the moon. The moon completes one cycle around the Earth in 27 days, so we know the period, you know, the time to complete one cycle around the Earth, and we know how far the moon is. Call this a little r, Earth-Moon distance. So from that time and from that distance, we can determine the speed of the moon around the Earth, and we know Earth and moon attract each other with that force. And using very simple Newtonian mechanics, we can calculate exactly what the mass of Earth is. I'm not going to go into details of how to do it. It's not important today. But that method gives us the Earth's mass. Not the mass of the moon, but mass of the Earth. So again, it's in the order of 10 to the 24th power. Okay, so that's how much Earth weighs. Okay, so Earth has an iron core, it has magma, and Earth is geologically active. There's volcanic activity, there are tectonic plates which are in motion. So Earth is still active. Unlike the moon, all right, which is our next object in our analysis. Now, Earth, we talked about Earth, let's talk about the moon. There are many moons in our solar system. I'm talking about our moon, Earth's moon, also called Luna. Okay, Earth has one moon. Some planets have couple, like Mars, but if you go to other planets like Jupiter and Saturn, you have 50, 60, 70 moons, right? So Luna is smaller than our planet. So the radius of the moon is also a sphere. Not the perfect, but okay. Let's not worry about that right now. Just a sphere with some radius. But that radius is approximately a 1/4 of Earth's radius. Maybe a little bigger than that, but approximately 1/4. And its mass of the moon is in the order of 10 to the 22nd kilograms. Actually, the mass of the moon is 1/80th of the mass of the Earth. All right. And how far is the moon? This little r here. That is 384,000 kilometers. Okay, remember Earth's radius was 6,371 kilometers. This is how far Moon is away from us. So the orbit of the moon is like a circle. According to Newtonian mechanics, these orbits don't have to be perfect circles. Actually, we have this shape called an ellipse. An ellipse has two focal points, and the object, in this case Earth, or if you consider Earth around the sun is at one of the foci, and then the planet or the moon goes around in an elliptical manner, okay? But I'm exaggerating the shape right now, okay? So both Earth's orbit and the moon's orbit are very close to perfect circles, but not exactly perfect. And that is the radius R, which is 384,000 kilometers. Now, Earth is much smaller than, Moon is much smaller than the Earth. And because of that, it can't hold the heat, okay? In the beginning, Moon was also warm, just like Earth is today, okay? I'm talking about the inner. So we don't have any volcanic activity on the Moon, okay? The latest one maybe was 200 million years ago, and it died, okay? That's because it's cold, and the reason it's cold is because it's small, okay? Size has to do with how hot the inner parts of the planet is, okay? Greater the planet, takes more time, longer the time it takes to cool off. And also, because Moon has a smaller mass, it can't keep an atmosphere, okay? Earth has an atmosphere, Moon has none. That's very important if you consider the surface of the Moon. The surface of the Moon is full of craters. A crater is the impact of the stuff that hit the Moon, right? Meteors, space rocks, anything you can imagine. When they hit, they leave their mark. Craters, you know, circular or different shapes. We don't see them too much on the Earth. There are some, you can find them, you know, but there aren't that many. The reason we don't find them is Earth's surface is changing. I mean, I'm talking about millions of years, you know, and rocks which used to be below now are above. All geology is, you know, based on how these rocks travel, right? But also, Earth's atmosphere is like a protecting shield around the Earth. So when those rocks enter the atmosphere with huge speeds, due to friction, they burn out. So by the time they hit the surface, they're just dust, okay? Only a few of them, you know, can survive. So it's not because Earth attracts less meteorites. No, I mean, these are random pretty much, and both Earth and the Moon, I mean, there's a size difference, of course, but that's not that important. What's important is the mass. Earth is massive, therefore it has an atmosphere, and the atmosphere pretty much finishes those rocks. And also, the surface of the Moon is very rigid, solid. There is no movement, okay? So whatever hits there, it stays there for billions of years. That's why Moon looks so different from the Earth, full of craters and dust. All that dust settles down, and that's what the Moon looks like. And the gravity on the Moon is very weak, okay? Like 1/6 of the gravity of Earth is on the Moon. All right? So, that much about the Moon. Oh, one more thing. There's only one face that we can see. All right, so let's go back to this picture here. Now, this part of the Moon we see all the time, meaning when the satellite is here, it's still the same side that we see. Why is that? Because just like Earth is rotating around an axis, Moon also rotates around an axis. But that rotation around its own axis and the Moon's revolution around the Earth has the same period. Okay, it takes the same time. So we never see the other side. Okay, so if this is the Moon goes around the Earth like this. Okay, there's always this side that faces the Earth. So by the time the Moon completes one cycle around the Earth, it has also rotated around itself just once. Okay, now imagine the Moon did not have a rotation around its own axis, then it would be like this. Okay? Then over the course of those 27 days, we would see all sides of the moon. All right? Everything on the moon. We don't do that. That's why they call it the dark side of the moon, right? Dark side. But this dark is only metaphorical. Dark side of the moon. It's not dark. It's just that we don't see it, okay? I mean, there's light there. If the sun is here, the sun shines on this side. Yeah, if the moon is here, well, this part may be night on the moon, but depending on the position of the moon around the Earth, the other side that we don't see will have sunlight, so it's not really dark. It's just that we don't see it. Okay, so much about the moon. It's smaller than, the radius is 1/4 of Earth's radius, and the mass is 1/80th of Earth's mass, and it's 384,000 kilometers away. The moon is important. We have our calendars made based on the moon, and also we have calendars based on the sun, right? So our next object in our planetary neighborhood is the sun itself. Now, sun is a star. It's a very hot object, okay? It's the source of energy in our solar system. It's made of mostly hydrogen. Hydrogen turns into helium. Okay, hydrogen is the gas or the element, let's say, with only one proton in the nucleus and one electron around it, and helium has 2 protons. So how do you go from 1 proton to 2 protons? You push 2 protons close to each other. They don't want to be together, but you push harder and harder, and you can only do it when there's a lot of mass, all right? Sun is huge in terms of mass. It's 2 times 10 to the 30th, okay, in kilograms. So the sun is not only large, the radius is about 109 Earth radius, but its mass is huge, 10 to the 30th compared to 10 to the 24th of Earth, right? So with that much mass attracting each other under the influence of gravity, everything feels a pressure, okay? Under that temperature or pressure, let's say, you have this nuclear reaction, which we call nuclear fusion. Nuclear fusion. Fusion means getting together. So 2 protons get together and become an element with 2 protons, which is helium. And in the process, energy is produced, which is the light that comes to us, the radiation, okay? Light is made of particles called photons, light particles, right? This is the energy that we get from the sun. So it's not a chunk of coal burning, which they used to think in the old days, in the 19th century, right? But it's nuclear fusion. So it's mostly hydrogen, which turns into helium, but this takes a long time. When the sun runs out of hydrogen, it's going to start burning helium, which means helium will be pushed to a proton, okay, and then higher elements, heavier elements will be formed. It's going to go all the way up to iron and all that. So, but that's going to take a long time, okay? I mean, the sun is less than 5 billion years old. For another 5 or 6 billion years, the sun will continue to use hydrogen, all right? So, that's what star is made of, the sun is made of, and that's how big the sun is. How far is the sun? How far is the sun from Earth? That's around 100 million or 149 million kilometers. Okay, this is the sun Earth distance. You can call it the orbital radius. Now this is not a fixed number, which means, remember the ellipse I was telling you about? So if I exaggerate it a little bit, okay, make it look more like an egg shape. So here's the sun. So there will be times when Earth is close to the sun, R1, let's say, and then there will be times when R is larger, call it R2, so R2 is greater than R1, or let's say Earth is farther away. By the way, that's called an aphelion. This point, the farthest from the sun, is called aphelion. Helios is sun. By the way, the symbol of sun is a dot in a circle. Earth was a cross in a circle. Sun is dot in a circle. So this is R dot M dot. Okay. And the time when Earth is closest to the sun is called this is aphelion, perihelion. I forget what it's called. Let me pause it for a second. Perihelion, I guess, yeah. I'll double check it. So that's the perihelion, I'm sorry, perihelion. Perihelion. Okay, so that number changes, okay? The Earth-Sun distance changes. Doesn't change too much. I mean, the more realistic picture would be like this. You have a perfect circle, but the actual orbit would be just a tiny bit different from a perfect circle, but it's still measurable, okay? We can measure this, or we can observe this from Earth. How do we do that? Let me talk about that for a second now. So there are a couple of things to consider here. When Earth goes around the sun, it also goes around itself, or rotates around itself, just like the moon, right? So let me draw this again. Now I'm looking at the orbit from an angle. So here's the sun, here's the Earth. Earth goes around the sun. Earth also rotates around its axis. That's how we end up with the night and day. But that axis is not vertical in this picture. The vertical line would be this, but it's tilted. Okay, we have an angle of 23.5 degrees. So when the Earth is over here, all right, that tilt is still there, of course. The tilt never goes away. So it's spinning like this. Okay. So if the Earth is here, it's spinning this way, while it's also moving around the sun that way, but it's also spinning like this. Okay, but it's just tilted. Actually, because of this tilt, we have seasons, right? When it is summer on this side, it is winter when the Earth is on the other side. Those seasons have nothing to do with the difference between R1 and R2. As a matter of fact, right now we are in January. We're close to the sun, actually. This is January. Okay, I mean, these days I think it's January the 3rd, and when it's July the 3rd, we will be at the aphelion, okay? But this has nothing to do with the seasons. Like if you were checking the aphelion and perihelion 1,000 years ago, maybe you would be finding them in March, okay? So those change a lot over the centuries. So Earth has this rotation around its own axis. and it's tilted. Now, because of this tilt, the daylight you will get in the summer is more. Okay, I mean, not just the amount of light, but also the time of the day. Okay, from sunrise to sunset, it's going to be longer compared to a daylight day in the winter. Now, how do we observe this from our perspective as observers on the Earth? Okay, here's us, and then this is a flat, let's say. We can see the horizon in all directions. Okay, so this is north, south. Let's imagine we're facing south. Okay, this is south. So back is north. The sun will rise from my left, which is the east direction here. This is the east. And this is what? West. Okay? And everything above me is like, what I can see is like a huge dome. Okay? I mean, there's no such dome above the Earth, but it appears that way. We call it the celestial dome. Or celestial sphere. Celestial sphere. Okay, and or the dome. Now, in the winter, the sun will rise in the east, but not exactly east, but a little south of east. It's going to rise, it's going to follow an arc in the sky. That's the apparent motion of the sun. In reality, remember, the sun is not moving. I mean, we are rotating, okay, around the Earth is rotating around its own axis. That's why the sun appears to be moving in those 10 hours or whatever, right? So it rises here. At noontime, it's not above us, but imagine a line from south to north. This line actually, which is called the meridian, in the middle. So you have equal on both right and left. That's where the sun is. Okay, you see the sun right there. That's winter. Actually, December 21st, that's the winter solstice. That's the position here at noontime, lowest in the sky. Because if you repeat the same experiment, in summer, in June 21st, the winter solstice, the sun will be right here. This will be the path of the sun. See, the rising place of the sun now is a little bit north of east. Similarly, when the sun sets right here, it's north of west. Okay, but that's the summer solstice. This is winter solstice. So any day in between the two, between June and December, the rising and setting places of the sun shift. Okay, go this way, go back and forth. It remains there. Of course, I'm talking about where we are in Houston, or anywhere in the U.S. It looks like this. If you're in the South America, equator, it looks different, all right? But you will never see the sun right above you in our location, all right? More on that later. So this is what the sun appears to be doing, and this is noon, 12 p.m., right? So imagine you repeat this every day. You just you have your watch and make sure you compensate for the daylight savings time, okay, because there is a 1 hour difference. Imagine you keep a watch in your house which you never play with. You always go with the 12 p.m. that you set at the regular time without the change in time. What will you observe, okay? What will you see? The sun will never be always on the meridian, that line, Okay, sometimes it'll be on the right. Right means west in this picture because you're facing south. And sometimes the sun will be at noontime to your left, which is eastward, okay, east of south. So, actually, this is what you will see. And there are pictures like this you can find on the internet. It's a shape called Analemma. Analemma. Its shape is like this. An 8 shape, okay? If you do it at noon, the center line is what we call the meridian. And then you remember you're facing south, so to your right is west, to your left is east. So depending on the time of the year, the sun will be here or there or there. So what they do is, let's say every other week they take a picture and then they superpose those pictures and you have these nice shapes, okay, of the sun. Now this shape looks like an 8, right? And that's because of this observation that we would have, which is a result of this 23.5 degree inclination. But it's not the whole story. It turns out that this difference between R1 and R2, pretty much R changes constantly because it's an ellipse, contributes to this 8, all right? How? How does it contribute? If it was a perfect circle, if the orbit were a perfect circle, not an ellipse, but a perfect circle, you would still have the 8 figure, but these two lobes, and remember that's 12 p.m., these two lobes will be equal in size, okay? You can see Analemma at any time of the day, okay? You can watch the sunset and take a picture every day before sunset and create your Analemma using those pictures. You'll still see that 8 shape, but maybe like this, okay? Tilted, or let me do it better actually, because I want this, 8 to look like this, all right? Or if you're in the southern hemisphere, it'll be looking like that. But the difference is, remember, these two lobes would have the same size if the orbit of the Earth was a perfect circle, okay? Y is not a perfect circle, a perfect 8, but this side is bigger than this. It's because of the elliptical shape. Now, I'm not going to go into very much detail right now, but just to give you an idea about why this elliptical nature has an effect on where you see the sun at noontime or any time you pick is relevant, is it goes like this. So, by the way, this Analemma, this would correspond to, normally this would correspond to winter solstice, this would correspond to summer solstice, right? Now, what does this elliptical shape have to do with the shape of the Analemma? Let's talk about that. I'm going to draw again the Earth. I'm going to exaggerate what happens in one day, okay? So here's the sun, here's the Earth. Now this is the path of the Earth around the sun, all right? Now it doesn't matter if it's a circle or an ellipse, it just curved like this, we know that much, all right? So the Earth moves in this direction, but Earth also rotates around an axis. We also know that. Let's say when the Earth is here, we look at the sun like the way I described. You face south and then find where the sun is. Let's say the sun is right above us, which is along the meridian. So we're here and the sun is right above us. Okay, that's what this blue dot here represents, the location of us. All right. Now, if the Earth rotates, and one day is one full revolution, we think, but it's not. Okay, one full revolution is not one day. It is actually less than a day. Why? Why? It's very simple actually. A 360-degree turn would bring that dot to here again, right? So imagine a line here which is parallel to this line. So one full revolution, which is 360 degrees, would bring this blue dot back to where it is, right? But that's not a day. This only takes 23 hours, 56 minutes, and 4 seconds. Okay, so about 4 minutes shorter than what we call a day, which is 24 hours. Why? Very simple. When you are here after 23 hours 56 minutes, the sun is no longer at the top, right? Very simple. I mean, look, this is how the line that joins the center of the Earth to where you are continues. This is the line. But this line shows you where the sun is. So actually, the sun is to your left. When you're facing south, the sun is on the east side of the meridian. The sun will require 4 more minutes, which means that Earth will move a little bit more during that 4 minutes, those 4 minutes. And now, when the sun is right above you, and you're here, okay? So this takes an additional 4 minutes, but if you think about it, this point has moved. How much? By some angle, all right? So 360 degrees plus some angle. Now that angle is actually close to 1 degree, right? But okay, I have to be careful here, not 1 degree. 1 degree is how far the Earth is moved in its orbit, because 1 year is 365 days, and 360 degrees is just 1 circle. So this angle is actually 1 degree, okay? So this angle is even smaller than it. It's noticeable. So the point is, Earth has to move or rotate a little bit more than a full revolution, and that's what we call a day. Okay, so a day is defined as the sun goes back to where it was yesterday, the day before. It's called a solar day, but the solar day itself, if it's just based on the apparent location of the sun, is not the same throughout the year, okay? This is called the apparent solar day. It's not useful because the watches we have, the time, you know, we can't afford it changing throughout the year, every day pretty much. So we need to use a mean solar day. What we do is we take the time around the sun and divide it to 365 days, you know, and we have a mean value. That's 24 hours, okay? There's that difference between the apparent solar day and the mean solar day. But anyways, it takes 24 hours, let's say, for us to have the sun above us. All right? Now let's see what happens at the other side, 6 months later. So I'm going to draw it again here. I'm going to exaggerate. An ellipse, okay? So here's the sun. Here's Earth, and here's Earth at the perihelion and the Earth at the aphelion, right? Now, in 1 day, Earth goes from here to there, which means that it's above us. The sun is above us. Good. and this takes 1 day, let's say. Again, I'm exaggerating this angle. It's much smaller than that, but I'm exaggerating to make a point, okay? This rotates like this. But remember, according to Kepler's law, and this is from Kepler, Johannes Kepler, who was a student of an astronomer, Tycho Brahe. This is after Isaac Newton, but still hundreds of years ago. He discovered that just by looking at the motion of planets around the sun. The orbits are ellipses, which means that the speed of the planet, Earth in this case, is not the same throughout the journey around the sun. So basically, here it is fast when it's close to the perihelion, and when it's close to the aphelion, the Earth is slow. So after 1 day, the Earth will be only here. See, I made the distance here smaller than that, right? And when this is happening, I mean, this doesn't have to be for 1 day. You can do it for 1 month or 1 week. As long as the times are the same, it's going to work. You look at this triangle formed here, and this triangle. They look different, but their areas are the same. Same area. Okay, it's called Kepler's second law. And Isaac Newton explained why this is happening using his theory of gravity, you know. But Kepler just observed it, and came up with a law. So when you're close to the sun, you move faster. So why is this important in our case, in the calculation of day? Now, if it takes 1 day or 24 hours for this point on Earth to revolve and come to here, so it faces the sun again. Now that speed around its own axis does not change throughout the year. Only the speed along the orbit changes. So this means that the point over here, which I'm going to mark again, let's say the sun is right above us, we see it. After 1 day, this point will be over there. Because remember, the rotation speed doesn't change, but the revolving speed around the sun changes. Since this distance here, the distance that the Earth travels along the orbit, the arc, is shorter than the other one. Let's call this S2. This distance I'm talking about, S2, compared to that distance, which is S1. S2 is shorter than S1, which means that after 1 day, after one mean solar day, the sun will be on your right. When you face south, the sun will be on the west of south. Okay, the sun will not be at the top anymore. So this contributes to the 8 pattern that I was telling you about. Now this would be the case when the orbit were a perfect circle. Now that it's not a perfect circle, the 8 looks more like this. Okay, so this side is bigger than that side. So, long story short, the elliptic nature of this orbit is detectable. And people have known about this for centuries. Okay? Alright, so that is the Earth's motion around the sun. The distance between the Earth and the Sun, which is 149 million kilometers, more or less. Now this number is important because it's defined as the astronomical unit, 1 AU, astronomical unit. And that's our yardstick when measuring distances in astronomy. Okay, 1 astronomical unit. Now, but we know that the actual distance between the sun and the Earth is sometimes greater than this number, sometimes less than this number, depending on where we are. Okay? Now, between the Sun and the Earth, we have two more planets. Between the Sun and the Earth, so this is 1 astronomical unit, I said. 1 AU. Now roughly divide this distance into 3, okay? So place another planet here, another planet. Okay, so roughly, not exactly, roughly, we have equal distance. These are the planets, inner planets, Mercury and Venus. All right, and there's also Mars here, the 4th planet from the Sun. Mars. Now I can't remember the exact distance from Mars to the Sun, but it's comparable, okay? So it wouldn't hurt. Maybe that's also comparable to the distance between Venus and Mars. Not too bad, okay? So the total distance could be 1.3 AU from the Sun when you speak of Mars. Now these are all rocky planets. They're solid rocks, pretty much. Earth, remember, has an iron core. So does Mercury, but Mercury's iron core is much bigger than, compared to the size of the planet, it's larger. Okay, let's put it that way. It's heavy, and then over long time, Mercury actually shrinks, okay, because of this mass. But it doesn't have a breathable atmosphere like the Earth. It's smaller than the Earth, so the mass of Mercury is 0.38 mass of the Sun. Venus, on the other hand, is comparable in size. This is 0.95 times Earth's mass. But similarly, Venus does not have a breathable atmosphere. Actually, it's very hot. It's full of volcanoes and the dense atmosphere, and it's very heavy. So there's a lot of pressure. High pressure, okay? So there's no way humans can survive on Venus. I mean, if you could go to Venus, your spaceship wouldn't even survive. There's so much pressure, atmospheric pressure. But recently they discovered on the higher layers of atmosphere of Venus, there's a probability of some microbial or bacterial life. But it's still an ongoing thing. But so if there's ever life on Venus, it's not on the surface, but in the upper layers of atmosphere. But in any case, it's not breathable, right? And okay, I think I made a mistake here. What I really meant was the size. Sorry, let me just go back a little bit. Let me erase this. What I really meant here was the size, not the mass. Okay, so I'm gonna change these to R. So the radius of Mercury is 0.38 of radius of Earth, and Venus in size is comparable to Earth. Right? So Venus is active geologically because of the active volcanoes. Mars has volcanoes and deserts, and it's smaller though, so the radius of Mars is 0.5 or 0.53 if I remember correctly. So it's smaller than Earth, and gravity on Mars is around a third of gravity on Earth. Now, after Mars, what do we have? We have the asteroid belt. Now let me zoom out here, okay? Now things are going to change a little bit when we get to things beyond the planet Mars and beyond the asteroid belt. So here we have around the sun, I mean it's everywhere around the sun, of course not just here but everywhere, the belt, the asteroid belt. Okay, many rocks around the sun traveling, and one of them is really big. We call it a dwarf planet, and it's the dwarf planet Ceres. Okay, it's big. There are many other asteroids, of course. Now, after the asteroid belt, now we have the giants. All right, this is the outer solar system. Now here comes Jupiter. Jupiter is huge, the biggest planet. All right, and now we have Saturn. Saturn is also huge. And Saturn is famous for its bright ring, okay? I mean, Jupiter has a ring too, but it's not as bright, but it has a ring. Now, the radius of Jupiter is 11 Earth radius. And Saturn is around 9 Earth radius. So both are really big planets. But these are not solid. These are made of gas. We call them gas giants. Okay, not only their size, but their mass is also huge. But the funny thing about Saturn is its density is less than water. So they say if you could have an ocean which would carry Venus, it would float in that ocean because its density is less than the density of water, and the buoyancy of water would lift Saturn up. But it's a gas, okay? Saturn has gas. And these planets have storms. And Jupiter is famous for the eye here. The eye of Jupiter, storm activity. And the eye itself is bigger than Earth, right? And Saturn is famous for a hexagonal shape pattern at the pole. Okay, beside this ring, there's this hexagonal shape in the pole. So these are gas giants, and we have we have two more large planets, and these are called Uranus, very cold, okay, cold planet, and Neptune. And these have ice, so not just ice, gas, ice, I mean liquid form, but also ice, especially in the core we have ice and rock, but these are called ice giants. Okay, Uranus and Neptune, so these also have rings, but these rings are not as bright as Saturn's rings. And the Uranus has an interesting property. Remember the tilt in planet's axis of rotation, like Earth is 23.5 degrees. Well, Uranus, guess what, is 95 degrees. So Uranus rotates like this around the sun. Okay? And then Neptune. Also, Jupiter and Saturn have many, many moons. Okay? Like 80 or 70 satellites. Okay? You have Io, Europa, let's list them, the famous ones. Io, Europa, Calypso, Ganymede, okay, these are all famous moons of Jupiter and Saturn, you know. So, Uranus and Neptune have those two. And after those, we have the Kuiper belt. So let's zoom out a little bit. So here we have another belt, which is even larger than the asteroids. We call it the Kuiper belt, and in the vicinity of Kuiper belt or inside we have our Pluto, which used to be classified as a planet, but we found a couple of more like Pluto, like Eris is one of them, and we have one called Makemake. There's another one like an egg-shaped, just like Ceres. These are called dwarf planets. Okay, Haumea, and there are other ones which have like numbers, which have names like numbers and letters. I can't remember, but these are called dwarf planets. Dwarf planets. All right. So Kuiper belt is like the asteroid belt, and we also have these dwarf planets. And well, this is like Pluto is so far from the sun. Okay, now let's talk about the scale here. From the sun to Pluto, this is 40 astronomical unit. Okay, remember, one astronomical unit, 1 AU, is the distance between the sun and Earth. So what I drew here is not drawn to scale. Okay, it's 40 astronomical units. So from the sun to, let's say, Neptune is 30 AU, and from the sun to, let's say, Uranus, that is 20 AU. Again, not drawn to scale. And when you go to Saturn, it's 9 or 10, let's say roughly 10. And then between the sun and Jupiter, it's roughly 5. Okay, I mean the 5 and 10 are not exact, but 20, 30, and 40 are more close. That's the scale we have. So the outer planets are not just large, but they're also really far from the sun. And we can calculate how long a year is on Uranus or Neptune easily, just by the distance from the sun, okay? According to Kepler's and Newtonian, Kepler's laws and Newtonian's law of gravity. So what else do we have? We have comets, okay? The comets are highly elliptical. Their orbits, like Halley's comet is famous, right? So a comet would be like this. Highly elliptical orbit, and the comet would be here, and the comet will have a tail. I mean, there's ice surrounding the rock, and the side that's facing away from the sun is where actually it's more obvious if the comet is really close to the sun. We'll leave a trail like this. Okay, that's due to the sun exerting a pressure. I mean, it's evaporating, and we leave we see the trail of the comet. Okay, so there are many comets, and sometimes it takes 100 years or more to complete one cycle around the sun. So that's our planetary neighborhood, and from now on we're gonna analyze this motion around the sun, the Earth's motion, and the moon's motion around the Earth in more detail, and see how our calendars are made. You know, it's a lot of history behind it. And then we're not going to go into too much detail about other planets, but we're going to study the sun itself as a star and other stars in the universe. So stars make galaxies, and galaxies clusters of galaxies. We're going to be focusing on the methods of astronomy and stars and galaxies. All right, it's going to be a long journey. This is a study of the universe, an observable science. It's like an experiment which was done long time ago, billions of years ago, at least 14 or 13.7 billion years ago, and we're still analyzing the data from that experiment, starting from the Big Bang. Okay, that's what astronomy and astrophysics is all about. Observation and trying to fit that observations to theories, come up with new theories. Okay, so till next time, goodbye.